Hello class, good morning. I'm happy to see you guys once again. I'm happy to have a class with you. In our previous lesson, we learned about algebraic expressions, and we learned how to represent numbers using algebra and how we can even find their unknown values using algebra. Now I want to know, in case I make, or in case you hear someone make a particular mathematical statement, how do you determine whether that statement is open, it's an open statement or is a closed statement? How do you even identify an open statement? An open statement always has no limits. It has no beginning, it has no ending. It can go as far as you can never imagine. It's not having any limit at the left nor at the right. And it's so open that it doesn't address a particular entity or a particular person or a particular range of numbers. Alright, so let's look at this mathematical statement and then find out whether they are open or closed. So, like I said, so for the open, it has no limit, but for the closed, it has limits. We know where it is beginning from and where it is ending. We know how it's starting and we know how it is ending. And for closed statement, they always address or talk about a particular entity, or they always kind of give a range of numbers, unlike the open statements. So now looking at these mathematical statements, we want to find out whether the first one is an open statement or a closed statement. She is a Ghanaian. She is a Ghanaian. This one is not addressing a particular person. If you say she could be your sister, your friend, your mother, your grandmother. So who is that she? The she here is a pronoun. It's not a noun. It's not addressing any particular entity. So maybe because of that, this statement, you cannot say it's a closed statement because it's not addressing a particular entity. So you have to conclude that this statement is an open statement. Looking at the second one, the boy is handsome. The boy is handsome. Which boy? Which boy is handsome? The boy is handsome. So let's talk about boys. You have many boys in your house, in the school, in your community. You have many boys. So let's talk about the boy. Who is that boy? So you see, for the open statement, they always come with a second question in mind. Anytime this statement is made, you always have a question sprout out in your mind that demands an answer. There will always be a who, a what, a when, a where, a how. So these are the things that you can use to determine whether a statement is open or closed. So looking at the second statement, it's asking us a question here. Who is that boy? So a who here demands an answer. So this can't be a closed statement. Ask the first one. So these are all open. Let's look at the third statement. Yao is handsome. Now we know Yao. Yao is addressing a particular person. So we can say that this statement is closed because it's not asking. This statement will not have to come up with a secondary question. But we know Yao is a name of a person, and Yao addresses a particular fellow or person. Now, so we can boldly or confidently conclude that this is a closed statement. What about the fourth one? X is such that x is greater than 5. X, we don't know x, we don't know the value of x. And we are saying that the way for x is such that x is greater than 5. Now, we have 6, we have 7, 8,000, billion, trillion, quadrillion. We have numbers which are beyond our imaginations, which are all above 5. So if I say x is such that it's greater than 5, what are you talking about? Is x 6? Is it 7? Is it 100? Is it 1,000? Is it million? We can't say. So this one brings up a question. We have many numbers more than 5. So which one are you talking about? Which one is the value of x? So this one is an open statement. Looking at the fifth one, x is such that x is greater than 1 but less than 10. You can see. So now we know where x will start from. If you have to list or write the values of x, we know that this particular thing is talking about a range of numbers. Because x is what? Greater than 1. So all the numbers greater than 1. We have 2. I mean natural numbers. We have 2, we have 3, we have 4, we have 5, 6, 7, 8, 9. Here, though x is greater than 1, it's less than 10. So we can't include 10, neither can we go beyond 10. So we just stay between 1 and 10 because x is greater than 10, but less than x is greater than 1, but less than 10. So we can write x is equal to, or the set of x. The set of x will be 2, 3, 4, 5, 6, 7, 8, 9. Then we stop there. We can't move to 10 because x is less than 10. So this time we can give us a range of numbers, and we can say this statement is closed. So to touch on it again, open statements always bring up a question in mind that demands an answer. Who, how, where, when. So these questions demand an answer. So anytime you read a mathematical statement and it's asking a question, or you can't figure out the particular entity the thing is referring to, then you have to just conclude as an open statement. But if it's addressing a particular entity, like the question, the third one and this one, we can say they are closed, or that statement is closed. Now we learned about algebraic expressions, where we learned that for an algebraic expression it contains letters, operational signs, numbers, and even sometimes equal sign when we have to find the particular unknown number. And here we have 2 unknown numbers. Over here we have 5 times a number plus 4 minus 9 times a number plus 3 times a number. We learned all that, how to represent mathematical statements in using algebraic expression. We learned all this. So we want to look at how we can add algebraic expressions, how we can add 2 or more algebraic expressions. So to add algebraic expressions easily, the first thing you have to do is to group them, group the like terms, group the ones that share similar features, or the ones that share a common variable or letter. Looking at this, we have 5x here. So we have to look through the expression and find out whether we have another term or entity that has the same letter as 5 is having. We look through this, doesn't have. This one has x. This, for the 3 and the 5, they are just coefficients. They can be any, they are just numbers. The main focus is on the letters, as we learned in our previous lesson. So now we have to group like terms. So we have to bring the 3 and join it to the 5 and group them at one place. So grouping like terms, we come to 5x, come and pick this one. And when you are picking the like term, you should include the sign. The sign matters very well. So now we are done with the x terms, the terms that have x. Now we have to move on to the terms that have y, the second variable. The term that have y, we have negative 9y. Then we look through whether we get another term that has y in it. That would be the 2y. For the 9y is negative, so we pick the sign and the term. You come to the one with y2, with the 2y, and that also has y. So that one too is positive, so it should come along with its operational sign, positive. After grouping the y with the y terms, we now move on to the constants, the ones that have no term, the ones that have no variable. We have 4 here, which is a constant. As we look through, we realize that we have also 7. The 4 is positive, so it must go along with its operational sign. Then the 7 too must carry its sign along. as you can see here. So after grouping like them, we then can easily add them because we can add 2 or more like terms. Because they are having xx, 5 and 3 are having xx, we can easily add them and merge them to get a single term out of these terms. So 5x plus 3x, you see that we are adding 5 and 3. 5 and 3 will give us what? 8. 5 and 3 will give us 8. Then we just have to, because it's in x, it must go along with the x, giving us 8x. For the 9, we have negative 9. Negative 9, and we have positive 2y. So here, negative 9, like I said in our previous lesson, anytime you see a negative number, a positive number coming up, you have to take the negative number as an owed money, a debt that you need to settle. So just imagine you owe someone 9 cedis, and now you have only two cedis on you, and the person has come pressing you that he needs his money right away. It's not because you have always been promising and failing. Today I'll give to you, tomorrow. Then the person comes in and says, Master, today is the day that I need to take all my money. And you have only 2 cedis on you. What do? You give me the 2 cedis. When you give me the 2 cedis, have you completely settled your debt? Or you still have an outstanding debt to settle? Look at this. We owe 9 cedis, and you're having 2 cedis. When you pay the 2 cedis, you still owe him 7 cedis. So in the end, the result will be negative 7y because you still owe him 7. And anytime you're owing, it's negative. When you're having the money or you're paying, that is when it's positive. So we still owe him, or you owe that person negative 7, and it must go along with its variable, which is something which distinguishes it from the other terms. It's very important. What about the constants? 4 and negative 7. You owe someone 7 cedis, and you have 4 cedis. How do you, when you pay the 4 cedis, you will still owe the person 3 cedis. So it must be negative 3 and not positive. So looking at this, here, this term is different from this. The same this one is different from this. So we can't merge any of these terms. So this becomes our final answer. Looking at the second question, the same thing, the same principle is applicable. Looking at this, we have 4x, we have to first group like terms. You pick 4x, you pick 3x, and you group them. Because they all have an x in them. You pick 2y, you look through, we have 5 also here. You group them. Then, here we don't have constants. I mean, the numbers without terms. So we just leave it like that. So looking at this, 4x plus 3x, 4 plus 3 is 7. Then the 7 must go with the variable x. For the 2y and the 5y, when you add them, you get 7. It must go along with the y, giving us 7y. So our final answer, because x and y are known, are different terms, we can't add them. So looking at the third one, we have 4x squared y. You have to be very vigilant here. 4x squared y. You can see that in this term, it is the x that has the exponent of 2. That has the power 2. Then we have 5xy squared. Here, the x is not having any power. It's the y rather having power. So these two are not the same. It looks similar, but not the same. So these two are not like terms. Looking at the third term, it's having the x power 2, but the y power 1. That is no power. We don't write this in math. So that means this first term and the third term are like terms. Look at the fourth term, negative 2x squared y. Here you can see that, it's supposed to be negative 2x y squared. Here we can see that, this one and this one are the same. Xy squared is, for the y is carrying 2. This one 2 is carrying 2. So these are like terms and these ones 2 are like terms. So when we add them, we are going to get 4x squared and the 3x squared. If we join these two terms, we get 7x squared. Then for the 5xy squared and the 2xy squared, they are all the same. They are all like 10 because x power 1, y power 2, y power 2. So we can merge them. When we merge this, we get 7x squared y. When we merge, we get 3xy squared. I hope you have questions in mind, and I'm very glad to hear you bring out those questions so that I can answer them as soon as possible. I will urge you also to read around, get books and read so many examples. Any example that's beyond you or which seems very challenging, bring it to me and I will help you out. I'll see you next time. Bye bye.